A very good morning to all. We have seen how the pandemic changed the world in the past 2 years, and researchers all over the world, including many of us here, started working on COVID-related research. Especially was interested in the transition from a healthy population to an infected state. So we also started exploring those questions, and I will present our findings today. Before I begin, I would like to acknowledge Professor Sujit, Ankan Banerjee, and Alan Verghese, and Dr. Lars Witting, also the organizers of this workshop, and the funding from DST India. So COVID-19 caused by pandemic SARS-CoV-2 has rapidly spread all over the world since the beginning of 2020 January. So we'll look at India's second wave. So the Delta wave in India was faster than ever expected. We can see here, during the first wave, it took 110 days to reach up to the peak of 97,000, starting from the number of cases around 8,000. Whereas if you see the second wave, it took just 62 days, which is almost the half, to reach a value of around 1 lakh. And so it was really fast. And we were not prepared for such a rapid increase of cases. And the hospitals were full. And then we were struggling for liquid medical oxygen, and shortage of drugs. And so exponential model was the commonly used growth model. That is like, we can think of it as like one infected person spreading to a finite number of people, and then each of them spreading again. The tree continues like this, which can result in an exponential spread. In other words, exponential growth was thought to be the defining characteristic of an epidemic in its initial growth phase. Then how did such a rapid growth happen in the case of the Delta wave? So I am showing the same figure. So in 62 days, it reached 1 lakh, but it didn't stop there. It went up to almost 4 lakhs cases per day. So the question I would like to ask, is there any signatures of such a huge rise hidden in the data from the data in the beginning days? Can we detect something and say there is a huge rise coming, so that it will be useful for the policy makers to implement appropriate timely interventions to minimize further spread? And first, we can check for exponential growth. The simplest test is to plot it in a semi-log plot. So semi-log plot exponential growth looks like a linear variation. And we did that. This is the plot of 7-day daily variation of COVID cases for third wave in UK, fourth wave in Germany, first wave in South Africa, and first wave in USA. So we can see a nice linear relation in the semi-log plot indicating the exponential behavior. In contrast, some of the waves showed a nonlinear behavior, that is something like a concave upward nature in the semi-log plot, and which is a strong indication of the waves growing faster than exponential. So those waves are called, such a behavior is called hyperexponential growth. And we can see that India's second wave was indeed hyperexponential. And there are also cases where you see slower than exponential growth, especially many of the first wave of these most of the countries. And then here the message is, we see all the 3 types of variation, not just exponential. And if you are to fit an exponential for these kind of nonlinear variation, it won't properly fit always. You have to adjust the growth rate. Something like a piecewise exponential has to be used. So, interestingly, we see that the hyperexponential wave was observed almost all during the extreme waves. That by that mean I mean in each country their worst waves were associated with a hyperexponential growth in the initial growth phase. These are some examples. Now exponential growth can be written as a equation like this, like a growth equation like this: di by dt proportional to I, where I is the daily new infections. And we saw that the exponential description is not an all-encompassing model for the COVID-19. So we present a general growth model where we can add one parameter m here. Di by dt is now proportional to I power m, and based on the value of m, you can integrate this and get three different solutions. So m equal to 1, this the second one is the just exponential solution. But when m is greater than 1, we get a power law which grows faster than exponential. And when m is less than 1, it is also a power law, but which grows slower than exponential. And this is just a simple integration will give all these. And k is the proportionality constant and c is the constant of integration. And we can see the power law exponent is alpha, which is related to m as alpha is equal to minus 1 by m minus 1. Now we'll concentrate on the first case where the solution is a power law which grows faster than exponential. So you can see here there is one term Tc. So consider t tending to Tc. This term will become almost, this will approach 0, and as m is greater than 1, alpha is negative. So that means this will go to infinity. So it is like you have you are going to have infinity in finite time. So hyperexponential growth has in finite time singularity. And from this power law equation, we can easily derive the expression for the doubling time. For example, for an exponential, it doubles at equal intervals of time, whereas a hyperexponential doubles at a doubling time, which is something like a geometric progression, and the doubling time shrinks as negative powers of 2. So it's like successive doubling time is reducing and rapidly approaching 0 in finite time, and you will end up seeing infinite number of doublings in finite time. So that leads to finite time singularity. And there are reports supporting that the doubling time is not constant in reality. And we have seen that India's second wave was indeed hyperexponential. So faster than exponential waves are like extremely hazardous, and we need to implement stricter measures to contain further spread of such waves. However, in reality, we are not going to have infinite number of COVID cases. In the beginning, it starts as a hyperexponential wave, but first of all, we don't have infinite population to get infected, and there are multiple other factors coming into picture. Once the wave begins, there are lockdowns and other interventions which will reduce the number of cases, and infected people getting immunity will reduce the number of susceptible individuals, and then the wave starts to deviate from the power law. It starts to slow down, and it becomes exponential or slower than exponential, and finally reaching a peak before it starts to decrease. So hyperexponential is unsustainable indefinitely. You can see it only during the initial growth phase. And if we were to fit exponential functions to describe a hyperexponential power law, you can see I have tried, but you need you have to adjust the growth rate to fit it. So better than that, we can use a power law. You don't need any adjustment of parameters in time. It is just one single parameter alpha, the power law exponent. And you can note that it has a TC inside this along with the T. It is a TC minus T. So you need to know TC. So what I do here is we can optimize for TC, and then this is the best power law fit. So these are two examples shown for the case of second wave in India and second wave in Italy. Now, another thing we can note here is, even though there is a very nice power law, we can see some fluctuations over the power law. And these fluctuations are not just noise. We have removed all the irregularities in observed in data by taking at least this 7-day moving average, but still there are fluctuations, and these are not noise. We should not disregard it as noise. We can use the concept of log periodicity to explain the origin of these fluctuations. So log periodicity is we can define it as log periodic oscillations are periodic oscillations in a logarithmic scale. So they appear as in periodic oscillations with increasing frequency. And then in the data of daily infections, it's not very easy to see them. So we can differentiate, and in the growth rate, we clearly see those oscillations. But how do we confirm whether it is noise or periodic oscillations? So we can take we can do a spectral analysis where you can input the time series as a function of log of Tc minus T. Then if there are oscillations which are periodic in log scale, it will appear as a peak. Here you can see the peak is significantly above the noise levels. And then by that we can confirm the presence of log periodicity in the data. And log periodic oscillations precede finite time singularity. At finite time singularity, these oscillations also, these are increasing frequency in time. So it will also have infinite frequency in that Tc. So we can make, how do we understand log periodicity? There is a power law, and then we multiply it with a log periodic sum, which is like a periodic function with arguments as a log x. So this can be written as, like, cosine functions can be written as real part of exponential. And now this can be easily rearranged and written as x power alpha plus I omega. That means log periodic power laws can be represented as a power law with complex exponent. So I'm not discussing the full derivation, but this is the final expression which we use for fitting. So here I'll explain the terms. The last term, this part is the log periodic oscillations, like just the oscillation part, and then you are multiplying with the power law to get that amplification in time, and then there is a extra term power law added, which will give you the trend. And now we'll try to understand what it means having hyperexponential growth and log periodicity in the context of COVID-19. So this is the growth equation we started with. Consider m is equal to 1. You have exponential growth, and the growth rate is a constant. Then you start with 1% infected, and then it doubles at constant times. So the number just doubles at equal intervals of time. Now we'll see what happens for a hyperexponential. So we simulate a pattern using this doubling time equation. It's like doubling time is becoming shorter and shorter in time. So we start with one infected person and doubles at these time intervals. But in reality, if you measure at a uniform time interval, this may look like a disproportionate growth. Like di by dt is not proportional to I. Like whatever number of cases today, if it is 20, we expect 40 tomorrow. We may not be seeing 40. We may be seeing example 100 or something. So this will appear as a disproportionate growth because there are multiple doublings occurring in short time as you go in time. So that is the way we can think how hyperexponential is possible, and not one person infecting like very huge number. This can be the one possible mechanism. And now how is the virus able to spread so fast? So there are some supporting evidence from literature saying that the virus SARS-CoV-2 is steadily mutating over the continuous transmission among humans. I'm not talking about different variants. In the Delta variant itself, during each multiplication, there are some mutations, and then those mutations actually help in increased infectivity. So in the last week, we do observe the similar behavior, like hyperexponential and log periodicity are not just observed in COVID, they are observed in variety of systems, like systems approaching some kind of catastrophe. Then the way the system evolves towards them follow a similar path. Then the examples are stock market crashes, where the before the crash we observe log periodic patterns. And another example is large earthquakes. Then it is observed to be preceded by small earthquakes, and it appears as a scaling up process resulting in like large market crash or large earthquakes. These hierarchy, okay, these are some more examples observed in engineering system and biological systems. Like we can see in the world population data also it is observed. And these hierarchical structures leading up to this catastrophe can be used to develop precursors to predict them. It is actually done in stock market crashes and earthquakes, and also we have done it for thermoacoustic system, which Ankan will be talking. And so we can say that dynamics of complex systems approaching a catastrophe has some generic features regardless of the governing physical processes. In summary, extreme COVID-19 waves exhibit a hyperexponential growth during the initial growth phase. And we observe signatures of log periodicity, which will potentially help better modeling of pandemic. And also we suggest that the mathematical models should not be restricted to just exponential growth. Instead, we should consider the general growth model. And we should also incorporate log periodic oscillations in epidemiological model. This would better match models with the real data, thereby enabling better predictions. Thank you. Question?
Yeah, question please. Question?
Hi, nice talk. So I have a question. You said that log periodic oscillations are seen in other systems as well. And you gave an example of financial crashes. So I'm not really convinced the fluctuations in a financial market would really follow a log periodic oscillation, because the frequency of log periodic oscillation will increase with time.
Yes.
And I don't think that's something that is seen, at least before a crash.
This is actually, I'm not talking about these high frequency kind of small oscillations. There will be a trend which is like building up maybe over the years.
Trend.
That trend, it might be over the years or something, not those small fluctuations.
But you said that it's seen in the hyper exponential increase, right?
Okay, we see in the case of COVID over hyper exponential. You don't need it to be hyper exponential. It can be just a power law and then overlaid with oscillations. But in case of COVID, we looked at hyper exponential waves.
All right.
Need not be.
Thanks.
The basic, okay, it comes as something like it comes as a power law, the correction to the power law. So I did not explain the origin of log periodicity. It's something like you can see there is a power law, and then power law is generally associated with some scale invariance. And then scale invariance means you see similar patterns in different scales. If you are observing the similar self-similarity at discrete scales, it means discrete scale invariance. And that needs some correction term to the power law, which will be this. I think Ankan is going to explain more about this, how it comes. Yeah.
Is there any other question? Okay. Since there are no questions, so let us thank Induja.